Cool. So, yep, this is the second attempt at this. So we have, if you found the blog, you've probably found the spreadsheet. So this is the blog where I'm going to get the spreadsheet from. And this link here is where you download the spreadsheet from. I've actually already downloaded the spreadsheet. I will open that just now. So this is the spreadsheet here. Just going to check, that when you get to that spreadsheet. And one of the things that I do for my spreadsheets is all of the cells that are that you can't put anything into are grayed out. So as I'm clicking here, there's no sort of cells that I can change. I would need to unprotect the sheet. So that's what I'm going to do, is I'm going to unprotect the sheet, and this is the password. So it's SIPBS and a lowercase c. So that is that sheet unprotected. I'm also going to unprotect the solution prep as well, and which is the same password, SIPBS MSC. And if you wanted to use this for your students, then you can maybe change the password if that's what you wanted to do. I'm also going to unhide here, and I've got another sheet called the error sheet. Now the error sheet, because the error sheet is hidden, then I've got no reason to begin to protect any of the cells in there. So let me take you through how this sheet works. The idea is that students have an opportunity to prepare solutions as they would in the lab. So they would put powder onto a balance, and here for this particular experiment we've got a range of weights that are possible. And the idea behind that is that students don't get an option to choose, say, exactly 600 milligrams or 0.6000, which kind of forces them into doing the calculation for themselves. In this second cell, there's a drop-down list for all of the standard flasks that we have available in our lab. So the students have an opportunity to choose a particular volume, and then they can name their solution, whatever they would like. So I will call this stock 1. Okay. So what happens in this row down here, the idea is that a student gets an opportunity to name a solution or to name the stock solution. So I'm going to take my solution here from stock 1. And I think what I will do is I will do a series of dilutions, a series of 1 and 2 dilutions. So I'm going to change that into a 10 ml standard flask. Call that dilution 1. I'm then going to take dilution 1, and I will again do a 5, 10. I'm getting a bit bored now, so I'm just going to call it D2. I'll take my D2 solution, and I'll do another 5 and 10, and I'll call that D3. And so what we're trying to do is get the idea here that students can make up their own dilutions, make up their own names, keep track of their own solutions, just as they would in a lab experiment. 5, 10, D5. And I think I'm just going to do a couple of 1 in 10s. 5 is my solution. I'm going to do a 1 in 10. Let's call that D6, and then I'll take the D6. So I've got a series of dilutions here, and I'm going to put a 1 in 10 in there, and I'll call that final. So again, one of the things that you don't see in this sheet just now, and I will show it a little bit later, is the calculations that are behind what the student has done here. So the idea is that in a real lab situation, the concentration of a solution within a standard flask doesn't magically appear on the standard flask. The student actually has to work out what the concentration in that standard flask will be, either from their experiment or perhaps prior to going to the experiment if they're doing a calibration curve. So what we've done in this sheet is hide all of the concentration calculations so that the students will only really see perhaps what they would see in the real lab. So let's go to the UV trace here, we've got here simulated noise, and I have on this list all of the different solutions that I've prepared. So I've got my stock solution. So as I put my stock solution in, it's obviously far too concentrated because I have an absorbance of 3. So that seems a bit strange. What I'm going to do is just move this this selector here is there. The idea behind the selector is that it gives students an opportunity to see what the absorbance at particular wavelength would be. So this is the absorbance at 288, or the absorbance is 3 at a wavelength of 288. So let's see what happens as I do dilution 1. Okay, well, I might possibly be coming into range, but maybe not that great. Dilution 2. Okay, still quite high. Dilution 3. Wow, dilution 4. I might have to do lots of dilutions here. Okay, so this actually simulates the real situation where if you had a concentration of solution that was far too high, you would just probably get a sort of a straight line at a really, really high absorbance value. Solution 5 and solution 6. Okay, so I didn't quite have the dilution factors that I expected. So what I'd like to do is I'm actually going to go back to my solution prep. I think I'm going to cheat slightly. What I'm going to do is, rather than re-prepare all of these solutions obviously in the lab, what I'd have to go back to is re-prepare my stock. And this is one of the beautiful things that I like about this sheet, is the fact that if a student does make a dilution mistake or a dilution and an error when they get to the spectrometer mimic, then it's quite easy just to go back and change the dilution values by perhaps changing 1 or 2 cells. It allows for a greater opportunity to make mistakes that the students have than perhaps they would have in the lab. Okay, so that's a little bit better. That's kind of what I would expect it. In fact, I would like it to be a little bit more diluted. So I'm going back to solution prep. I'm actually going to set it to 1000, which I think is the biggest size. Okay, brilliant. Okay, so let me go back to my stock solution. It's still quite high, and then I can bring these dilutions down. And this is exactly the sort of thing that you might see in a spectrometer experiment. Just this gradually coming back into range. So let me focus on the orange arrow here. We could perhaps ask students, what would the absorbance be at the minima? So students would have to go through it. So let me 339, 337, 34. So this is the minima here at 312. And then you might ask them what the wavelength at the maxima would be. I think that would be 350, but by the looks of it. So it would be 350, it would be 350. Yes, it would be 350. And let's, in our experiments that we do, so this is modeled on potassium dichromate. And what we do here is we, let's just take a look at what we've got. I think it's 257 is what we use. 257 is what we use. So that is the interface as far as the students see. So let's see some of the design behind this, spreadsheet, and I'm going to go to solution prep first. And what I'm going to do is I'm going to unhide these rows, unhide here. That's them all. Okay. So the way that I've set this spreadsheet up, let me go to formulas if I can. I think, yes, this should work for formulas. So I've now swapped over to the formula options here. I'm just going to try and expand these a little bit. Oh. Let me just see. Okay. And okay, brilliant. Out over this side, these are just quite simply the drop-down list. So I've got a drop-down list for pipettes, for standard flasks, for the option masses, and also for the solution list names. All these really represent is what these drop-down lists would be. Okay, so I'm forcing the students to enter particular values here. And because I'm forcing students to enter particular values, then I need to fix that cell on a drop-down list which I think if I go, where is it? Let me see if I can data validation. So I've gone to the data tab, I've gone to data validation, and you can see here that I am allowing a list in that cell, and I've got a drop-down source here. I'm going to click this, and it will take, this is my drop-down list, my available drop-down list. Okay, so I'm just going to close that down, cancel that. I also need a drop-down list for all of the solution names, which is at the end. So I've got an equals list here. What they equal is all of the names that a student might use, in this case, solution 1, D2, D3, and so on and so forth. So again, because I've moved all of these, students can change these values, but that then changes the list of names in the solution names list, which then changes the names or the list that's available to the students. Okay, so what we are trying to do now, so this is one of the things that we did for this spreadsheet was that we originally had a spreadsheet that just quite simply did what the dilution that the student recommended was. So if it was a 10 mils and a 100 mil dilution, then it would quite simply be a 1 in 10 calculation. But as we looked at it, with myself, my colleagues, Dr. Breen and Dr. Akil, what we decided was that we really wanted to do in this lab was try and mimic some of the real dilution errors that students would come across. And so what we've done here is this is set up in such a way, so this is actually what's called an H lookup function. So what we have in this H lookup function is that we are looking to this error spreadsheet here. So it looks for this value. So this H lookup will look for this value 5 in the error spreadsheet. Okay, so let me go to this error spreadsheet here. And what it's going to do is it's going to look up this pipette value 5, and then it is going to go down this column here, okay? It's going to go down that column. So the question is, how far does it go down the column? The problem that you've got is that you need to have some way of making sure that this spreadsheet, that this H lookup doesn't always read the same value, because that doesn't give the student any experimental error at all. So the way that I've set this up is that it actually looks at this row value here. Okay, so what it does is it will return what we call return the value, depending, it will count the number of rows and it will return a value from the row. So for example, oops, sorry. So for example, here you see this row value. Well, that row statement just here with the open and close brackets will return the number 8. Okay, here the row will return number 9 and so on and so forth. Okay, and so this is exactly the same. This is what it does in this sheet here. It starts to look through this list. We'll go to row 8 here. Okay, the row index number. Okay. So what this does is this actually forces, rather than having a 5 ml pipette, it will have a 5.055 ml pipette. It's exactly the same principle here, but this time, instead of looking at rows, you're now looking at, instead of looking at pipette volumes, you're now looking at standard flask volumes. And so here you can see the pipette volumes with the errors, and here you can see the standard flask volumes with the errors as well. And so then this final column, which is here, which actually works out the concentration. In this case, the concentration, I think, is mg per mil. Yeah, mg per mil. So what now happens is it looks up the concentration, the value of this cell here, and what it does is it looks up the concentration value which is already calculated. and then it will multiply it by the dilution, the pipette volume, obviously with the error included from here, and the standard flask volume with the error included in here as well. Okay, so what I'm going to do, I'm going to go back to the figures, and maybe having some figures might be useful here. So here, what we can see is that rather than a 5 ml volume, it has selected a 4.9914 ml volume. And instead of a 10 ml volume, it's taken the 10.0147. So this includes the errors in the standard flasks that you might have. And then, so it's actually multiplying. So this is a VLOOKUP with the concentration. So that will be looking up the stock 1 solution in this list, looking up the stock 1 solution in this list, and then taking the concentration here. Okay, so that will be taking, what that is basically sort of saying is 0.0, what this cell here is saying is take 0.0607464, multiply it by 4.9914, divide by 10.0147, and work out that concentration. And it just does this for the whole row. Okay. The way that this error sheet is designed, the formula is actually stated here. Now, Excel has, perhaps this is rather frustratingly, Excel has what is called a volatile random number generator. So you will see that each time I change my value, so concentrate on this cell here, each time I do any calculation on the spreadsheet whatsoever, that value will change. What that means is that whenever a student perhaps looks at a UV spectrum, if they were to change the this wavelength selector here, the spectrum would actually shift slightly because the random numbers on the spreadsheet would always be regenerated, and we didn't want that. So the way that we've handled this on the error sheet is by generating all these random numbers using this function here. Okay, rand between. So it's rand between the size of the glassware minus the error, and the size of the glassware plus the error. So we have this formula in every cell in this block. And then what I quite simply did was I used the copy and paste value function, so that is a list of random values, but it's now fixed. It's never going to change. It was a little bit more tricky. Let me just, for the UV traces, so let me unhide, because we've got a random number generator in there. So let me unhide these, and I'm going to change the font here so that it's dark. Let's change it back to black, just a little bit clearer. Brilliant. So what we've got here is, in actual fact, what I'm going to do is I'm actually going to hide these cells so that it becomes a little bit more, I don't normally need to do that, but it just becomes a little bit more visible in terms of what I'm doing. Let me shrink that just slightly. Okay, I hope this is still visible. Okay, so these are the wavelengths. This is just quite simply incremental values. This is a noise function. So in one of the other blog posts that I will put up, I'll discuss this random noise generator. It's a modular equation based upon these values here. So this is the noise generation parameters. Now, what I'm doing to generate this noise is I'm actually taking the length of the name that the student provides. So here the student has provided the name D3. I'm working out the length of that, and I'm also working out what the ASCII 2 character of the last letter for the name would be, as well as the vial row. And I actually just feed those values into it. And they're just values that I've selected, not quite at random, but I figure that a student is going to always perhaps have will perhaps change the name of their solutions to 1, 2, they might call it dilution 1, dilution 2, dilution 3, dilution 4. So my assumption is that if I use the last letter, or if I randomize according to the last letter, then the student will hopefully always get a different set of randomized values for every vial name. It's not going to work if a student calls it one dilution, 2 dilution, 3 dilution, 4 dilution. It's just not going to work that way. But I couldn't cover every eventuality. There is also a vial row number here. Let me just see this. There is vial row number, solution prep. That's, yeah. What I also have is, let me just see how that, yes, okay. The prime is a key factor in working out the modulus, because the way that the randomizer equation works is it needs actually a high value prime number. It's the same kind of idea that's used in modern cryptography as well, but we're not using it for that purpose here. And then you have a multiple value, and that multiple value contains what the vial row number would be, what the last letter would be, what the name length would be, and importantly, what this replicate number would be as well. What I'm going to do is I'm going to change this to, if I can find the blank solution, go all the way up to the blank solution. So that's just noise, okay? What I wanted to get, or what we wanted to get, was the noise to change every time the student did another replicate, okay? So that is why, I go down to D6, it might be a little bit more obvious, okay? A little bit like a real experiment. Every time the student does a replicate, then they will get a slightly different set of noise values, okay? So that's what we wanted to mimic as well. And so that's why the replicate number is there. The replicate number was also there because what students were finding that they had to do is if they wanted to do a replicate, then they had to set that up in the solution prep sheet. And that was quite long-winded, whereas in actual fact, you would take your solution to the spectrometer and you might take 3 or 4 measurements on the same solution. And so that's really what the idea of a replicate number was, therefore. So this calculates the trace value. So these normal dist, if I just highlight that, that is the equation for a normal distribution. And in this case, it's a normal distribution based around an average wavelength of 257 and with a sigma value or a standard deviation value of 30. And in this one, normal distribution is exactly the same thing, but this time the mean is at 350 and the standard distribution would be 20. And I've just quite simply modeled those so that they fit what I would expect a dichromate, a potassium dichromate curve to look like. Oops. Okay, so these are then what I am calling the raw absorbance values. I will need to try and find out just where. Yes. Okay. So, excuse me. What was happening here? I just need to remind. Yes. Okay. So, what the raw absorbance values are is they are adding together the noise trace as well as the proper UV trace that actually sits on top of it, so that what a student actually sees is not only the trace itself, but also the noise values. Then what we've tried to do is we've tried to add this non-linearity. So what happens is when you place a value, a vial in a spectrometer, because what you're getting is absorbance, and absorbance is the log of a ratio. When you get to really high absorbance values, you're getting to very, very low transmittance levels. So what we find is that if you end up with a transmittance value of, say, perhaps only 1%, the absorbance ratio would be 2. Just the way the mathematics works, because it's a logarithm of a ratio. So what you find is that at really high absorbance values, the instrument can no longer measure the amount of light that's actually getting through the sample. And so we have this non-linearity, which is built into this. What basically happens is I'm taking the absorbance value, I'm converting the absorbance value into transmittance, and then I am adding, I think, 0.1%. And so what's happening there is that it makes sure that the absorbance value will never go higher than 3. And that's a realistic simulation of what a student would find in a spectrometer. So that's this sheet nearly explained. The only other thing, I'm not quite sure what those values are there. I think they're just lag over values from something else. The only other thing to look at here is these lambda values. And what I am doing here is, let me just check why I am, I need to try and work out what, so I just need to work out where this is coming from. It's AG17, which is that one. I suspect that this value is a lag over from a little piece of coding or something like that. That maybe shouldn't be there. So what this is this arrow or kind of spin bar control is there so that students have the option to scroll through the trace and to choose a wavelength. There might be easier ways and faster ways of actually doing this, but it actually works out quite well for, it's not unreasonable that for some simple spectrometers, you will quite literally have to scroll through all of the values. And then what I wanted to do was to actually return what the lambda value would be here. And the way that that is done is by, I'm definitely going to have to check why these lookup values are set the way that they are. So what we have here is another VLOOKUP value. So the way that this VLOOKUP value works is that it is going to look at what the lambda value here would be in this column. When it looks at what the lambda value is in this column, it will then look at this whole table and it will find the value in the 5th column here. So it will work that way. I'm not quite sure why that's got a 0.09 in there. That is, I'm gonna perhaps have to try and check out, looking forward on the sheet, why that's there. I may have put it in for another form of calculation some time ago, but that's how that works. So so that's really it in terms of explaining the sheet. I hope if you're using this sheet for your labs or your students, then you find it useful. We're distributing it under Creative Commons, so all of the information is on the blog about there. Just hope you find it useful. There's no charge, as I say, because we're distributing it through Creative Commons. Although if you could let us know if you find it useful, that would be quite nice.